Welcome! In this series of videos we will look at topics common to both the PowerBasic console and Windows compilers. Today we will look at the definition and use of numeric variables. In this series of videos we'll be covering topics which are common to both the PowerBasic Windows compiler and the PowerBasic console compiler. In order to do this, I've set up a small common library to allow us to display information on the screen from a program regardless of whether you're using the Windows or the console compiler. There are three basic functions in this common display library. There's prep output, log, and wait. The prepare output function takes a console name as a parameter, an X and a Y start coordinates, and optional rows and columns. Since this code is designed to work regardless of whether you have the console or the Windows compiler, we're using a conditional if statement, which is handled at compile time, to test if we're actually inside the console compiler or not. So you'll see in here there's an if def pbcc32, which if that's set up we are in the console compiler, and it will prepare the functions accordingly. If we're in the Windows compiler, the same three functions will be prepared, but internally they'll be slightly different. So for the console compiler, we're using a standard console window, and for the Windows compiler, we're using a text window. Today's video will be looking at numeric variables. What we're going to do is to declare a number of variables within this function, the first which will be an integer variable. Doing this, we have now declared the variable called count as an integer. Now, traditionally in BASIC, you could quite happily declare the variable like that, with the percentage sign at the end, which would declare it as an integer, and it would work quite happily. As so. However, what people tend to do now is declare variables like this, usually with a prefix of the variable name to indicate later on in the code when you're actually using the variable what type it actually is. So it becomes more readable and you don't get confused between integer variables and string variables. Now, an integer variable can hold a whole number in the range of between minus 32,768 to plus 32,767. This is a fairly wide range and can be used for many things. However, most people in PowerBasic tend to use the long variable. The main reason for this is that while the long variable can actually handle numbers very much larger, up to 2,000 million plus or minus, long variables tend to be handled more efficiently in a 32-bit system, especially PowerBasic. So you very rarely actually see anybody use integers. Integers admittedly do take up less memory than longs, but most computers these days have so much memory that memory constraints are rarely a problem. Should you need a very, very large number that is beyond even what a long variable can actually handle, you can actually use the quad variable type. Now, as you will see from help, the quad variable type can handle significantly larger numbers, probably beyond anything you'll ever need to do. They have 18 digits of accuracy. They do come with a cost, as in they do take 8 bytes for each variable you've got set up, but again, most modern computers have so much memory, this is rarely a problem. If you come across code which uses the suffix approach to actual integers, these will be useful constructs for you. Percentage sign indicates that it's an integer, the ampersand indicates it's a long, and two ampersands indicate it's a quad. Other variable types you're likely to come across are the currency and extended currency variables, which are quite common for use in financial transactions. You can see we've set up the amount 1 as a currency variable, the bit amount 1 as a currency X variable, and these are also exactly the same. How these are actually used would appear like this. If we're putting in a value into the amount, this would put a value of 245.565 into amount 1. Now the easiest way of actually doing that is to put the @ sign immediately after it, and for the second one, 2 @ signs. This would indicate that we're only interested in the 2 decimal places, but we would actually store this to more than 2 decimal places. We could actually store it up to 4 digits of precision after the decimal point. For most things you normally do, unless you're doing a lot of financial transactions, you won't be using the currency variables much. If we put these out to our log, and since these are numbers, we'll translate them into strings. And if we run the program now, there you'll get information put out quite happily. If we added an extra decimal point to that, it still prints out with just the 2 decimal points, so it basically ignores anything after that. So worth bearing in mind if you're looking at fractions of a penny or a cent. The other numeric variables that are worth looking at aren't variables at all, they're constants. You will need constants occasionally in your program where the value is going to be set at compile time and is never going to change, and you don't want it to change for the duration of your program. In order to do that, you'll basically set your constant up by specifying it with the type of the constant before the name. These are usually done right at the beginning of the program, even before your first function is executed. And if we compile that, now it will compile quite cleanly. And anytime you want to use it, what happens is at compile time, when you compile this program, any reference to the test constant will be substituted into the code. So if we put something in here to add this on, and we'll turn this back into a string. If we run this now, it would put the value 1 in. Quite happily, because that's what you set the value of constant. The way it works is any mention of this constant within the code is replaced with this value at compile time. So this construct would not exist after compilation. Another numeric variable you will see actually mentioned through code, especially in the Windows compiler, is Dword. This is very often used to reference handles to window objects. Mainly the reason is this is a double word, so it's a 32-bit 4-byte unsigned integer with a range of between 0 and 4,294 million. Basically twice the size of a standard long. This is very useful because in Windows anything referenced as an object tends to be handled as a Dword because it's unique throughout the entirety of Windows. You don't see as much use of these in the console compiler, but if you do need a very, very large long value, then a Dword will do nicely. They are also very useful for indicating absolute memory addresses, such as used to store pointer values. As an illustration of the efficiencies in using longs over integers, we can perform a simple test. Now all we're going to do here is we have declared a local variable as a long, and we're going to basically iterate around it 100,000 times. And all we're going to do is increment another long value by 1 each time we go around it. What we're going to do to test this is we're going to set up a quad variable which is going to count CPU cycles. And we will use the ticks command to initialize the qcount variable. And after the iteration, we will end, and the value left in this will be the number of clock cycles, which we can then put out to our log. And if we run that now, it tells us we took 731,535 clock cycles to actually run through that. So let's do the same thing, only this time we will do it with a integer variable rather than a long. So we'll copy our code, and we'll use an integer variable. And we'll run the code now. So you'll see for the integer it was actually slightly longer in clock cycles to actually run through exactly the same piece of code. Now another variable type that you may occasionally use is a byte variable. Now a byte variable is basically an 8-bit 1-byte unsigned integer, which will allow you to store values between the range of 0 to 255. Now while they are very small, they don't take up much space. If you're doing a for next loop like we did before, we'll find that these are actually even less efficient than the integer. So we will compare both of these, one using the byte and one using a long. So we will steal our long code. Looking at the output of a for next loop, when using a byte type variable, we can see it takes longer than a long. Also the fact that they only go up to 255 means that it's not going to be a very big loop. But they are less efficient than using a long. But certainly byte variables, if you only need to keep numbers up to say 250 odds, then they are very efficient in space. Now the other type of variable to consider are the floating point variables. If we're looking to declare a floating point variable as a single, we can do as so. Now, single precision floating point variables, as you will see from the help file, they are very versatile in that they can contain decimal points and have quite a wide range. However, the downside of single precision is that they are limited to 6 digits of precision. So it's fine if you are interested in the first 6 digits, but anything after that, then obviously it starts to use rounding. For some types of calculations, this can work perfectly well. It really depends on what your code's trying to do. As with other variable types, it does have the suffix on the end of the variable. which in this case is a exclamation mark. So if you come across any variables defined in that manner, then you know it's a single they're talking about. There is also the double position floating point, which is more flexible, which has a greater range and is accurate to a greater degree of precision, between 15 and 16 digits. It does of course take up more space. These can be defined as so. So if you see any variables ending in a hash sign, you will know that they are double precision floating point. The final one to look at is the extended precision floating point. Internally, when it comes to calculating, all floating point calculations are performed inside PowerBasic to extended precision. This allows 18 digits of precision, which again is probably more than you will ever actually need. To define these, you do as so. So if you see any variables in code with 2 hashes after it, these are extended precision floating point variables. So that's covered most of the common numeric variable types within both the console compiler and the Windows compiler. Thank you for watching.